First, the reduction, independent set and vertex cover. The independent set problem, which we introduced as one of our 4 representative problems in Chapter 1, will serve as our first prototypical example of a hard problem. We don't know a polynomial time algorithm for it, but we also don't know how to prove that none exists. Let's review the formulation of independent set because we're going to add one wrinkle to it. Recall that in a graph G equals to VE, we say a set of nodes S, which is a subset equals to V, is independent if two nodes in S are joined by an edge. It is easy to find small independent sets in a graph. For example, a single node forms an independent set. The hard part is to find a large independent set since you need to build up a large collection of nodes without ever including two neighbors. For example, in Chapter 1, of nodes 3, 4, 5, the problem of finding the largest independent set in a graph G. For purposes of our current exploration in terms of reducibility, it will be much more convenient to work with problems that have yes-no answers only, and so we phrase independent set as follows. Given a graph G and a number k, does G contain an independent set of a size at least k? In fact, from the point of view of polynomial time solvability, there is not a significant difference between the optimization version of the problem, find the maximum size of an independent set, and the decision version, decide yes or no whether G has an independent set of size at least a given k. Given a method to solve the optimization version, we automatically solve the decision version for any k as well. But there is also a slightly less obvious converse to this. If we can solve the decision version of independent set for every k, then we can also find a maximum independent set. For given a graph G on n nodes, we simply solve the decision version of independent set for each k. The largest k for which the answer is yes is the size of the largest independent set in G. And using binary search, we need only solve the decision version for big O of log n different values of k. This simple equivalence between decision and optimization will also hold in the problems we discuss below. Now, to illustrate our basic strategy for relating hard problems to one another, we consider another fundamental graph problem for which no efficient algorithm is known. Vertex cover. Given a graph G equals to VE, we say that a set of nodes S, which is subset equals to V, is a vertex cover if every edge little e in capital E has at least one end in S. Note the following fact about this use of terminology. In a vertex cover, the vertices do the covering, and the edges are the object being covered. Now it is easy to find large vertex covers in a graph. For example, the full vertex set is 1. The hard part is to find small ones. We formulate the vertex cover problem as follows. Given a graph G and a number k, does G contain a vertex cover of size at most k? For example, in the graph in figure 8.1, we don't know how to solve either independent set or a vertex cover in polynomial time, but what can we say about their relative difficulty? We now show that they are equivalently hard by establishing that independent set is polynomial time reducible to vertex cover, and also that vertex cover is polynomial time reducible to independent set. This will be a direct consequence of the following fact. 8.3. Let G equals to VE be a graph. Then S is an independent set if and only if its complement, V minus S, is a vertex cover. Proof. First, suppose that S is an independent set. Consider an arbitrary edge E equals to VE equals to UV. Since S is independent, it cannot be the case that both U and V are in S. So one of them must be in V minus S. It follows that every edge has at least one end in V minus S, and so V minus S is a vertex cover. Conversely, suppose that V minus S is a vertex cover. Consider any two nodes, U and V in S. If they were joined by an edge E, then either end of E would lie in V minus S, contradicting our assumption that V minus S is a vertex cover. It follows that no two nodes in S are joined by an edge, and so S is an independent set. Reduction in each direction between two problems follow immediately from 8.3. 8.4. Independent set is polynomial time reducible to vertex cover. Proof. If we have a black box to solve vertex cover, then we can decide whether G has an independent set of size at least k by asking the black box whether G has a vertex cover of size at most n minus k. 8.5. Vertex cover is polynomial time reducible to independent set. Proof. If we have a black box to solve independent set, then we can decide whether G has a vertex cover of size at most k by asking the black box whether G has an independent set of size at least n minus k. To sum up, this type of analysis illustrates our plan in general, although we don't know how to solve either independent set or vertex cover efficiently. 8.4 and 8.5 tell us how we could solve either given an efficient solution to the other, and hence these two facts establish the relative levels of difficulty of these problems. We now pursue the strategy for a number of other problems.